Good, yeah, okay.
Okay. Folks, just got this. Yep. Okay, well, it's not, so you need to give us and track for the material sciences department. Some max, there was a bachelor's in Berkeley, Princeton, and he had advisors in Kennedy and educated. So it's one of the these are interested in was a part of giving us the invented something called organic vapor jet printing, which is something that specializes in say where we use. And he's been in the human sciences department. One step awards that include the case of which one of them is the case, and then the other is the following these co-founding couple of companies and development for scale and like so
Great. Nice big room. I hope you sold enough tickets to this to justify the rent. You guys paid a lot, right? Okay, so I'll start kind of from afar, and then as we get toward the end of the talk, hopefully some ideas will, come to you about how this might be interesting to use in naval applications. I'm very thankful, obviously, to Mahesh for inviting me to be part of this forum, part of this working group. I'm very excited about the possibilities after several discussions that we've had. We've even written a proposal on some of these topics. But I'll tell you kind of the origin of my interest in this space. And hopefully that'll also give you a sense of kind of how I think about things, how I approach some of these problems, so that, when we get together to think about new ideas, new solutions, we, kind of have a good, productive, free-ranging discussion. So at the time, I was working on solar cells. Mahesh mentioned that I did my PhD in an electrical engineering group. So I trained as a chemical engineer. I was always interested in semiconductors. Ended up moving to Princeton to do a PhD in organic electronics. And mostly it was about technologies to make OLEDs, specifically to deposit the thin films and make pixels that comprise these displays. And it turns out that, now it's kind of a really useful, interesting application of things that used to be just kind of in people's imaginations, 20, 30 years ago. And I came to Michigan, and soon after I came here, I started applying some of those ideas and concepts in the realm of solar energy harvesting. And of course, you try to make, let's say, devices, and you battle things like low efficiency, and you try to improve efficiency and talk about lowering costs, which of course we at universities seldom know anything about in terms of real costs. But improving efficiency, okay, you could do that. And the thing is, as much as you battle trying to improve efficiency of solar cells, there's one big thing that plants often do that our solar cells seldom do, which is to tilt to follow the sun over the course of the day. So sunflowers do it, right? Trees actually have leaves that flutter in the wind, and that helps expose, on average, more of the leaf surface to sunlight. But our solar panels tend to be stationary. Now, you've seen, obviously, solar panels, and there's some here on North Campus, that tilt over the course of the day. And of course, you may have seen pictures, or maybe in real life, you've seen heliostats that involve concentrators that also tilt to follow the sun. But those systems in practice turn out to be very, very expensive. And people don't use them because you spend a lot of money trying to create the mechanism by which you're going to do that. And not only that, you have to prep the ground for it, and you have to run the cabling and everything else to the house, and that just actually increases the cost. So you're faced with a trade-off between throwing away almost 40% of the energy that you could harvest by following the sun, right? So you could make more money selling it to the grid, for example, or storing it in your batteries and not having to charge your electric car in the parking lot over here. Although it's nice to have a free parking spot, or open parking spot in the middle of the day, right? And the cost of the upfront cost that you invest into installing this kind of thing. And so we have a trade-off, right? And here it's kind of a simple trade-off that involves cost. Oftentimes in design, you actually encounter these kinds of problems. They're problems that are fundamentally rooted in some kind of trade-off. You want thing A, you want thing B, and the two compete with each other based on some kind of resource that's needed to make it happen, right? So that's a framework, that's a backdrop where this stuff starts. So if I look now, okay, so what does it look like quantitatively, and then in terms of the actual mechanics of it? So if you're looking at things from the standpoint of the sun, at zenith, at noontime, you see the largest projected area of the solar cell. And as you go into the afternoon and evening, you see progressively less and less of the solar cell, right? That's just simple geometry, trigonometry, right? If you tilt the panel, then the sun sees more of the area. Simple, right? Now, if you, let's say, log the instantaneous flux of sunlight onto the surface of the panel, the number of photons coming in per second hitting that surface times the energy of each of those photons, right? You have this energy flux and the total amount of energy per unit area. So the per second, right? So that's the units of power density, power per unit area. So that's what we've plotted here is the instantaneous power density hitting the surface of the panel, kilowatts per square meter. And you can see that you have a peak, as we said, at noon, at zenith, let's say you're in the equator, that's where the peak is going to be. And if you don't do anything, you have a sharp roll off. And there's obviously a formula for calculating what that is. And this is, yeah?
Zoom doesn't seem to be showing your slides. It's showing the top.
Let's see, let's try this again.
They can hear you, but there's slides on the background.
Can you see the blank screen now or the? Yep, good. Okay, let's try this and see if it works. So are the slides advancing? Okay, perfect. Apologize for that technical issue. So far, so good. Now, if you tilt the panel, you extend your captured power curve into the morning and the afternoon, right? And so the comparison between non-tilting, which is the blue here, and the tilting, the green, shown in these superimposed curves on the right. And if you integrate the area under the curve, that's the amount of electricity that your amount of energy that you're harvesting, and hence the amount of electricity that you can make and measured in kilowatt hours that you could then sell at some price that you, let's say, agreed upon with your utility if you're pushing power into the grid when you're not home. So you can see that there's a pretty substantial difference, and it's something like in the order of 40%. Okay, so here's our trade-off now. You either do this in a ground-mounted installation, okay, or you put it on a rooftop and then it's stationary. You can't do the tilting, right? So you have to choose between these two extremes, and over half of the installations, the power installations, that's your market size, is rooftop. And then even ground-mounted installations oftentimes don't do the tilting because it's just costly to get the machinery in place. And you can imagine these panels are pretty big and pretty heavy, so you have to have pretty heavy gears, and you have to have big motors to turn those gears, and the whole system just kind of ratchets up. So that's typical. We have this conflicting desires diagram. The two desires are listed here. On one hand, we want tilting. On the other hand, we want something slim. And then we're gonna want to have our cake and eat it too. So what do? There's actually a very common TRIZ. How many of you are familiar with TRIZ? Or TIPS, theory of inventive problem solving? There's actually like an algorithmic way of finding solutions to problems, provided you phrase the problem in the right kind of way. It was developed decades ago by some guy in the Soviet Union who looked at a ton of patents and he saw patterns, and he developed approximately 40 techniques that you could apply in this way. But it's a little bit arcane. Not some people know about it. If you look up, there's a Wikipedia article on it. Some people know about it, some people practice it, but generally not many people do. But it turns out you can look at a situation like this, and if you phrase it in the right way, a solution just sort of falls out automatically. One of the most common techniques is miniaturization of the elements and repeating them to do that. And this is actually what's happening here. So we just take the projection here, and what we have is an array of tiny little solar cells that are tilted. And now you get something that's slim. You just have to hook them up and tilt them simultaneously. Okay? But now we have to get a little bit practical. If you have all these tiny separate solar cells, you have to connect them, so that you're trading one kind of mechanism for another. And you also have to make a whole bunch of other connections. And so you might imagine costs start ratcheting up in some other domain of assembly, manufacturing of this thing, right? What if we could do this and again, break this trade-off between having many little elements that you have to synchronize and actually have something that's very simple to make, that's just like one thing that you're going to make, okay? So we can do something like this. So we take a flexible sheet, and then we put cuts on it. And it's a system of cuts that basically all the cuts are parallel to each other, except that the unit cell consists of two cuts that are offset relative to each other. Okay, so it's a two-atom basis of a unit cell. If you've ever taken crystallography, you maybe recognize the idea. And it does this weird thing. And it's a tiny little element shown here that's just a laser cut piece of plastic, Kapton in this case. And it turns out that, you know, we know how to make, at that time, we knew how to make thin solar cells that would be just layers deposited on flexible substrates, and they work pretty well, and they're resilient, and they can undergo these kinds of deformations thousands and thousands of times without suffering. And so we got intrigued by this. And what happens is that it turns out that there's a very good analytical relationship that you can develop between the angle of tilt of each of these elements and how much you pull on it. And the important thing, as far as our application is concerned, is that the entire thing stays very slim. What's the thickness? What limits the thickness of this thing, actually? How thin could I make it? How would I do that? Well, in the limit, let's say if the element went completely vertical, facing completely sideways in plane, what would set that height? Just the width of the cut, right? So the closer the cuts, the better you do it. It turns out that there's an additional advantage to putting the cuts closer to each other. And it has to do with calculating the projected area. And we realized this when we started doing these calculations. So as you might imagine, you have a sheet like this, you pull on it, and it begins to neck down in the middle, okay? Actually, all materials do this. Almost all materials, I should say, do this. If you take a rubber band and you stretch it, it gets thin in the middle, right? What is the ratio of how much it thins down to how much you pull it called? Poisson's ratio, yeah. French guy, named after a fish. Poisson. Yeah, Poisson's ratio. And it's got a minus sign in front of it to reflect the fact that all materials, pretty much all materials do this. Okay. We went ahead and we did some geometry on this and calculated how much it necks down for any extent of pulling that you do. And that's a plot of transverse strain versus axial strain. And of course, the slope of this curve is your Poisson ratio, okay? And also you can then calculate, analytically, you can calculate what the angle of the feature is going to be. So now we have our tracking algorithm, okay? Now, it turns out that one of those things depends on the cut density, if you will, how close the cuts are spaced. And the other one doesn't. Weird. So here you could see that the angle depends on the length of the cut, but you can define a cut ratio. And I'll kind of skip to the final message here. I'll skip all of this calculation here. What you see here is that Poisson's ratio does depend on how closely the cuts are spaced. Okay. And you can see a plot of Poisson's ratio over here versus axial strain. So for very densely spaced cuts, actually, the amount of necking that you get is very, very small, almost zero. That's really good for our application. Why? Because remember, we're not just tilting this thing. All we're doing is we're stretching, right? And so then the sun sees something like a projection. But if it necks down, we're losing that area, aren't we? Okay, so it's better if we don't neck down. So this allows you to keep the width the same essentially, but change the tilt angle. It's kind of weird. Now, the other, and so you can see here Poisson ratio versus the cut ratio as we define it. Okay. But the other thing changes, which is how, so it turns out that that cut ratio doesn't impact the feature angle as such. The feature angle is a function of axial strain for that symmetry of cut, Actually is a universal curve. And how far up the curve you ride does depend on the cut density. So the denser the cuts, the further up this curve you can ride and tilt these elements closer and closer horizontal without ripping it apart. It's kind of weird. So now you can define, because you know what the area looks like from the standpoint of the sun, right? You can now define an optical capture efficiency, the optical efficiency of this structure. And so we have this optical efficiency, eta sub c equals, that's the angle of the sun, and that's the tilting that you end up doing effectively by stretching this element. So great. I go to my colleague's office. We were making organic solar cells at the time, and at that time the efficiency wasn't very high. Now efficiency of these organic solar cells is up like 20%, rivals pretty much any other material system. At that time was on the order of 10%. Like, well, you know, there are some systems, some semiconductor materials that allow you to make solar cells that are 30% or more efficient, but they're super expensive. But well, this might make it a lot cheaper, right? Because we're gaining almost 40% extra electricity, right? So I go to my colleague's office, colleague in electrical engineering who makes high efficiency gallium arsenide, very thin solar cells that they can put on substrates like this. And I said, Steve Forrest, give me your best gallium arsenide solar cell. He says, why? I said, I'm going to cut it. Why would you do that? I said, well, take a look at this. So if we do this, this is a calculation now. If we do this, look how close we can get to a conventional tilting panel, except now we don't need all this extra height and all this extra mechanism and everything could stay very nice and thin. So finally convinced them to do that. We actually adapted that cut geometry and the manufacture of the actual semiconductor device on top of it, such that they used a special epitaxial liftoff technique that required some holes to be made for etching. And so we made sure that those holes are coordinated with the cut locations. So everything actually worked really well together. Laser cut the substrate, you know, transfer the solar cells, or rather transfer the solar cells, then laser cut them. And these flexible high efficiency solar cells now wind up on these kirigami substrates. Kirigami, by the way, is a Japanese art of cutting, as opposed to origami, which is Japanese art of folding. Okay, so that's kind of what these things look like, and they work as advertised. And you can do this hundreds of times, thousands of times without degrading the performance, because the semiconductor that's on it is extremely thin. And if you stay within the elastic regime of the structure, right, because as you splay this out in the corners of the cuts, you're getting quite a lot of stress, right? And it's being bent a lot. And so if you do too much, you can imagine that you could even rip the structure, right? That's not elastic anymore, right? So if you stay within the elastic limit, you could do this forever. It doesn't fatigue. Incidentally, making the cuts closer together and making those elements into very, very thin beams allows you to stay in the elastic regime much more easily. So everything kind of starts working together here. Okay. And that's, okay. So we were very excited. We even tried to start a company based on this technology. And then cost. And so I learned a few things by trying to start a company. I had this idea that this would reduce cost because I would use less expensive semiconductor to gather a given amount of electricity. So, okay, that's great. It turns out that there's this thing called bankability. Anybody know what bankability is? So, by the way, cost of solar power is, okay, there's a cost of the module. There's balance of system cost, which is battery, inverters, and everything else that has nothing to do with the actual solar cell. And then there's also the cost of putting it in and orchestrating the permits and getting the contract signed and everything else. And everything is kind of like 1/3, 1/3, 1/3 of the total cost. So even if I take the cost of the actual solar module to zero, or in this case, maybe I'm trying to reduce the cost of the semiconductor in the module, you still have all these other ones, right? Okay, a little bit tricky. And bankability is another interesting thing because the really profitable solar installers tend to work at very large scale, and because of the economy of scale, they reduce the cost of materials and contracting and crews and everything else to realize higher margins. And the other way in which they realize higher margins, because they're competing with other utilities, right? Because eventually the government subsidy is going to go away. The other way in which they reduce their costs is that they go to a big bank, JP Morgan Chase or whatever, right? And say, okay, we're going to install so many megawatts of solar. We need some cash up front to go and purchase all these panels from the manufacturers and to get the contractors lined up and rent all the vans and cranes and everything else and go install this stuff. Give us money. And the bank says, well, how do I know you're going to pay me back? Says, well, we have all these contracts set up with the utilities and they're agreeing to buy this for 25 cents, 10 cents per kilowatt hour, whatever. And by the way, we know with really good certainty when the sun is going to come up and when it's going to go down. We only have a few millions of years worth of data on that. Well, weather influence that, but so they think, oh gosh, this sounds like it's almost as reliable as a STEM job, right? It's almost, it's almost as a sure thing as like a professor, tenured professor working at a university generating income. So maybe not. I don't know. Maybe like I can't say this right now. I don't know. So they're like, okay, fine, we'll give you a loan. And because it's such a secure thing, right? We're not going to charge you a very high premium on the interest rate. So they need everything to work for 25, 30 years out, right? It's like your home loan, right? If you don't have a steady job, it's really hard. Well, there was a period of time when it didn't used to be that hard, but it ought to be really hard to get a very low, percentage, right, on your loan. So it's kind of the same. So that's bankability. And how does this impact your engineering? Well, your engineering is impacted because they, to ensure that the solar cells will live for 25, 30 years, they send engineers, consultants out to the factories to inspect everything and make sure that everything is tip-top, in good shape, and is super reliable. And the minute they see things like cuts and moving parts and things like that, they say, there's a risk factor here. And that cranks up that interest rate just a little bit. And it could mean millions of dollars on a project. Easily, just like that, right? So your So you're thinking, okay, increases the risk profile, the return on that risk has to be much greater than 40% better in this case. Because remember, that 40% is of the semiconductor, which is of the module, which is of the total cost. Oh, shoot. Here we thought we almost doubled the, how much in energy you could get. It's amazing. It's super. I mean, if you look at the curves of efficiency, which is basically how much electricity you can gather in the day on solar cells, and these curves, progress from your perspective, like they go up and to the right, a little bit like this, like this, like this, over decades. And then basically overnight, publishing this paper, we did this. But nobody cares. It's weird. So, okay, how do we do better than that? So there's these kinds of things, and there's concentrators, right? In which case the cost is really in the reflectors, and the cost of the semiconductor itself is super, super tiny, because now the ratio of the thing that gathers the sunlight to the thing that actually converts it into electricity is really large. And so what if we could come up with systems like that using the same design principle? So we try, and so we miniaturize. So with another colleague, PC Ku, in electrical engineering, and his student Chihui Chen, we started playing around with paper to create these little collectors and stick them on top of like little bent pieces of paper. So what's interesting is that if you take this piece of paper, for example, and you bend it like this, imagine now pressing on the left or the right shoulder. What you see, what do you see happening to the writing that's on it? Okay, so you see what's going on here? So now it's facing up, now it's facing sideways. So let's make a whole array of these things. And down where this wave of these sinusoids are, that are the support, we're going to put a frame, and this frame is going to slide and push on each one of these simultaneously. And the support looks like this. So that's where the solar cell goes, and then the little concentrator, the collector, goes on top of that. So this is a non-imaging concentrator. Okay, so here's one element of that, and we tilt it, and look, you can change the orientation pretty well with a finite displacement. And because you can array it now, I can make an array as wide as you want. The total amount of displacement is very small. So we still keep the same idea. And it's actually even better than the kirigami thing, because the kirigami thing, you have to extend it, right? So you start with a finite size, and then all of a sudden it gets that much smaller, right? No very lots of nonsense. Okay. And it turns out this works. So you get some optical concentration. I think the area ratio here was about 10, and this was made out of like super cheap metallized mylar. And so the reflectivity is not as good, and so like this is really cheap, but already you're getting sixfold. So it's not just, oh, we're just improving things by 30-40%. We're saying the amount of semiconductor you need to use now is down by a factor of 6, not down by 40%, factor of 6. And make little arrays, and they tilt. Sorry about the image quality here. And okay, it works. Now we say, can we push it even further? Can we take down the price of the high efficiency solar cell to 0? For this, we need to look to imaging concentrators, and these are really, really big arrays, right? They install as this building sometimes. And then you miniaturize that. So this is now a sheet of plastic. Actually, the way the process goes, we took 2 sheets of plastic. One gets molded, vacuum molded, into little parabolic dishes, like that. We deposit metal on it. Another sheet gets copper lines and solar cells. This is a tiny solar cell. It's a few millimeters in size. Put on it. The 2 get aligned, and we come in with a laser and cut. And the 2 actually fuse together at the same time as the cuts are being made. And then you splay it out. And so you have this sort of thing that tilts. And this way you can get concentration ratios that are really, really high. You can see here, this is the unconcentrated solar cell behavior, and this is the concentrated solar cell behavior. I don't know if these curves mean much to you. This is the current that it's generating against the load, and this is the voltage at which it works against that load. And so you can see, you can get like factor of 80 concentration here. But the angle to which you can tilt that is a little bit limited. I won't get into a lot of details. So then we tried to solve that problem. And here, what we do is we take these same kind of ideas of having cuts, parallel cuts, and now we impart some rotational symmetry to the cut structure, okay? Boom, 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 like that. And then you can number them or whatever. And then we actually push it out of plane. Okay, what the hell are we doing that for? Well, if you now slide the bottom portion, if you slide the bottom portion, you see that there's an imaginary line that connects two of the saddle points that are created here, and that thing tilts. So now we just have to hook up our optical element into that imaginary line to bridge the two things. As you can see, the tilt angle here versus displacement. You're like, well, this is kind of finicky, right? Like, oh, we dropped this, that, and the other. Well, it turns out that you can also parallelize the construction of this thing. So here's an array of these things because you just cut them out of a single sheet, and you can mold it so that it supports its own weight. Okay, and there's your optical element with the solar cell and the contacts coming out, and when you tilt, you can track the sun. In this case, it's a 60-degree solid angle. Okay. But nobody cares about solar cells, it turns out. Even with this, when we were starting to work on this stuff, there were several companies that were making very high efficiency, 40% plus solar cells. They were extremely expensive. And the only application for that was in space. And then, and the reason is that you want more power per unit weight of sending things up, right? So it used to cost how many dollars? $20,000 per pound to send things up into space. And then Elon Musk starts working on SpaceX, and SpaceX lowers the cost of launch. How? How do they lower the cost of launch? Huh? Reusable rocket. How is that? Why did people do that before? Why did I mean, simple idea, right? Just reuse the rocket. Don't discard the stages. Why couldn't people do that?
It's hard.
Why?
Patient.
Okay, so when you land it, right, what you're trying to do is you're trying to balance a stick on its end, right? That's what you're trying to do. It's a really hard controls problem. So you can put thrusters on the tip of the rocket and at the bottom, but keeping it aligned is a really hard controls problem, and you have to do your calculations really, really fast. So it's only when computers get fast enough and cheap enough and compact enough that you can coordinate all of that stuff. Moore's law, it turns out. So they did this. So the cost of launch came down from $20,000 a pound to $1,000 a pound. And that meant that you could send cheap silicon solar cells into space. And people, all these companies that used to make these high efficiency things were like, oh, there goes our market. That's one problem. The other problem is that subsidies ended and adoption for regular ground mounted installations wasn't happening enough. So by the time we came out with this and we said, look, you can effectively increase your production capacity in megawatts, right, or what measured in watts, by a factor of almost 100 by using our technology, it was too late. There were dead bodies everywhere. These companies went out of business. So timing is also important, and it doesn't depend only on how fast you work. If we worked on this, a year or two earlier, maybe we would, but by the time we tried to make a bunch of these things, you couldn't buy enough of these solar cells to make it work at a price that would have made sense. So it's weird. So instead of decreasing, the price went up because all these people went out of business. Okay. At that time, we started a new project. This gets a little bit more closer to Navy stuff, maybe. This is a picture of an electric eel, and it turns out and there's a lot of fish that do this. and a lot of other organisms, is that it generates a dipole, an electric dipole in its body. Okay. And a lot of fish do that, and they do that for sensing purposes, like in murky waters and so on. They could actually see around obstacles. They could sense what's below the ground, level of, so to speak, the bottom of the river or lake, using electric fields, projected electric fields. And so if there's an object that differs in its dielectric constant, for example, from the thing that it's hiding in, it can sense that. Weird, right? Now, the electric eel, the other thing that it does is that it can generate quite a high voltage by this mechanism, and it does it by polarizing what are called oocytes, not oocytes, electrocytes, in its body that are lined up from head to tail. So it's like a whole bunch of batteries, like little 2032 cells that are stacked up together. And the thing is that there's no polarity, but then it sends a signal through its nerves to polarize the cells. And what happens is that there are semi-permeable ion membranes that are separating these components of a cell, and you develop a potential very quickly, and it synchronizes it from head to tail. And what happens is all of a sudden there's this huge field, right? And the field lines, electric field lines, are projected outward from the eel. And if there's prey, it gets, the field lines short through the prey, and the prey goes into convulsions. And then the eel knows where it is and goes in for the kill, because the prey can't move, it can't swim away. It's convulsing. Okay, so it shocks. The shock doesn't kill the prey. The eel's teeth kill the prey. But the electric shock is what immobilizes it. So a colleague of mine, Mike Meyer, in BME here, we had a project, and one of the things, he's like, let's make an artificial analog of that. And the idea was to take these hydrogels and stick them into a tube, and then the hydrogels with semi-permeable membrane ion transporting hydrogels separating them would then take the ion-rich hydrogel, right, and allow one of the ions to go in one direction and the ions to go in another direction. And so you would generate these dipoles across the interfaces. And so you create something like that. There they are colored just for being able to see it. Otherwise, they're kind of transparent color, no color. And you get pretty high voltage. So it's a few millivolts for each, tens of millivolts each, and then it eventually starts adding up. It's like, okay, that's great. Problem is, if you want to get power out of this, it's really hard, because power is, I worked in an electrical engineering group for 6 years as a graduate student, and I learned that power is voltage times current. Okay. Anybody watch Star Trek? Why can't the Borg learn Ohm's law? Because resistance is futile in contact. We're old. It's like silly references, they don't work anymore. Okay, so the issue is that power is current times voltage. So voltage, yeah, you get voltage, but now you have to have current, or you actually have to have flow of ions, right? For the eel, the shorting happens on the outside, but here we're going to try to extract power. It's only for a short amount of time. So if we actually need current out of this stuff, we need to transport ions, and ion transport is really slow. And you can look at the size of these things that are millimeters. That's a really long distance for ions to travel. And so you need to shorten that distance. So we want to do something like that, and we could actually fold paper to help that. So that's the idea. You line them up like that, but instead of bringing them together this way, you bring them together by folding. And they're shown here as spheres, but you could really have very thin films to actually do that. And not only that, you can create structures, folded structures that are that are able to bring a lot of the elements together at once, because the polarization happens by physical contact here, okay? And when you do the physical contact, you need to synchronize all of the elements coming together. And it turns out that there's a folding pattern called the Miura-Ori pattern, okay? Named after a guy, Miura folding, that looks kind of like this. and it turns out if you ever find an old fashioned paper map, the paper map is actually folded in this pattern. So you pull on two corners and everything comes apart. It's really amazing. And certain leaves are packed into their buds. And then when they emerge, they unfold with very high fidelity. And the fold pattern is actually this. So it's really interesting. We did this, and now the gels themselves could be very, very thin. It all comes together at once. And what happens is before you would have very high internal resistance. And so the maximum power you could extract was very, very low because of that internal resistance. Now the internal resistance is very, very low because transport length is very small, and boom, your power goes way up. Okay, that's interesting. So maybe we can follow up on something like that. What else? The other interesting thing you could potentially do here is fluid surface interaction. And this is where we start to potentially get into the metamaterial aspects of these things. For now, these are just interesting structures. There's no metamaterial aspect to it as such. Now, here, what happened was my student, Aaron Lemro, went to aerospace, Dan Hinman, and his student, Lauren, and they stretched one of these Kapton skins, kirigami skins, over an airfoil, and they stuck it into a wind tunnel. And as you could imagine, as air flows over this at high speed, you develop turbulence, and that turbulence begins to interact with the surface. And now the surface responds in some way. And we actually don't know really like exactly what's going on at the microscopic level, but there is some suggestion. And of course, now if you stretch it to different amounts and there's a different amount of this thing protruding out of the surface, that there are changes in skin drag, at least, that are measurable that result from this kind of stuff. And so what they're telling me is that you could in principle use this to delay stall at takeoff, and that could be interesting. And of course, the other thing that's going on is if you think about the characteristic length scale for the turbulence patterns for the vortices, you could potentially tune the length scale of these cuts, right, and the elasticity pattern on the surface to respond to that. Yeah. Oh yeah, what did I say? Oh, darn it. No, we published this now. We published it. That's an old slide then. Yeah, that's a published paper you could actually see now. So it wasn't published here. Boom, now it's published. And so you can, these kinds of things I mentioned before, using this for solar cells. But actually, the other thing that we did here was to make a kind of wearable sensor. So it turns out for these rotationally symmetric patterns, you can think about this as a topo map, as a topography type of map that. If you look at a hill on a topo map, you see these iso elevation contours, right? So now let's say you start making cuts, you take a razor blade and you go in these iso elevation contours and you make cuts, but you don't cut it out completely, you kind of stop just short and you make a whole bunch of them. And then you push out. And it turns out you can get it to conform to some kind of three-dimensional envelope shape. And you can get pretty much any shape you can mimic this way. And the reason we got interested in this, because my group was working on a bunch of devices, and obviously now with the solar cell stuff, we're kind of looking at integrating semiconductor type functionality, films and devices with flexible substrates. What happens here is quite interesting, because if I have, let's say, some curved object, and I want to measure things on its surface, if I take a sheet and I put it over that curved object, I get wrinkles, right? Now, why would I want to do this? Well, there are all kinds of things that I want to sense on flexible things. We'll talk about this in a second. But the way that I create my electronic devices, it typically uses two-dimensional patterning on sheets, Kapton, silicon, glass, whatever. All of our patterning technologies completely optimized for 2D shapes. And so, again, we have a trade-off. On the one hand, I need it to be very nice and stable in 2D in order to create the pattern. On the other hand, I need to be flexible in 3D in another instance. And the two can't converge because of this wrinkling problem. And what this allows you to do is you initially define your circuit, right? Let's say circuit and circuit elements on a flat sheet. And provided they're thin enough, you can let this then go in and cut and let this thing drape over the surface. And there isn't wrinkling. Okay, so this here is a very, very simple, like the simplest imaginable demonstration of what this can do for you. This here is a strain gauge. It's just a commercial resistive strain gauge. It's a super, super thin serpentine piece of copper sandwiched between two pieces of plastic with leads coming out. And you measure the resistance of this piece. And if it sits on a surface and the surface stretches, the length of this serpentine piece of copper increases. And so its resistance, electrical resistance goes up. And you can just detect that. So buy off the shelf, $10, even less, put it on. And this is sort of what happens. So now this is my student Erin. What I'll walk you through this in a second here. So what she's got is the sensor on her shoulder with athletic tape over it to make sure it conforms, and leads coming out, and the wires are hooked up to a parameter analyzer that just measures the resistance. It's as simple as that. And she's wearing position markers and doing this in a motion capture studio in kinesiology on Central Campus. And I think it was Deanna Gates's lab at that time in kinesiology. And so she's moving it around. The camera system is capturing what we call ground truth, what is called ground truth, what the actual limb positions are. At the same time, the parameter analyzer is capturing the electrical signal, the resistance of this thing. And so the change in the resistance is mapped as a function of time, and the true position is mapped as a function of time. And then the two are overlaid. Okay. And what you get now is one pattern is from one strain gauge, another pattern is from the other strain gauge. And as the arm moves, you're mapping this kind of stuff. And it turns out that different kinds of motion produce different kinds of patterns. And you can capture all of that. And so you can put as many strain gauges as you want. And the more accurate you want the position to be, the more strain gauges you would put on there. But it's not that bad. Like it's simple, right? We know how to pattern these things and make them by the millions in minutes, right? In principle, if we're scaling this up. Now we're working on a wireless version of this. So these are strain gauges. There's 4 of them around, and in the middle there's some circuitry, and a little chip gets plugged into this. The student undergraduate who worked in my lab, blanking on the first name. It will come to me. Last name is Darling, material science and engineering student, working with Aaron Efke, wearing that device on the shoulder, and the cuff just holds a battery. So we didn't spend a lot of time and money trying to miniaturize all of those elements. We know that that could be done. Like if you have your Apple AirPods, right, that are wireless, you know that this could be miniaturized quite a lot. Yes, question? Oh, okay, right. So the other interesting thing to do, okay, so we think that this whole thing could be made quite cheaply, like on the order of $10 a piece. If not even less than that, and then you could start doing things with it. And it turns out that there's a lot of needs in physical therapy, sports performance, rehabilitation, even robotics, control, haptic feedback, and so on that could benefit from something like this. And now we have this sort of this approach of making sensors that conform to the shape of the body or something like that, or other kinds of shapes. Now, all right, what about different materials that we could potentially use? Well, so this is interesting. I hope the video plays here. Here now, this structure, this kirigami structure, is made out of a polymer that has shape memory properties, meaning that if you heat it and deform it, for example, it'll hold that, and then cool it, it'll hold that shape. And it'll be elastically deformable in that shape, so it'll hold that shape ostensibly. And if you heat it again and bring it back to its original shape, it'll hold that original shape. And you could do this back and forth, back and forth, back and forth. Okay, so here it is, that original shape gets put into hot water, and you can see it gets super floppy, and you pull it apart. Now it cools and it sets. Okay, now it just holds the shape. Yeah, see, it's load bearing. And now you could do it again. And there's metals also that do this the same thing, and of course could support much greater loads. You can go back and forth. So we think it's kind of interesting. There's also potential for actuation. This is a piece of plastic that you can buy at Joann Fabrics, probably. It's called Shrinky Dinks. It's basically polystyrene film that's been stretched, and the polymer chains are aligned in it. Now, in a crystalline kind of way. When you heat it, the polymer chains are now overcome by entropy, and they want to disorganize. And what happens is that they kind of ball up, but that pulls the sheet together in that area where that's happening. Okay, so what do we do this? What are we going to do with this? So imagine now I take a marker and I draw a line across this sheet. And then I shine light onto the sheet. The black line absorbs light and it heats up locally. So that's where the polymer chains shrink, and it creates a hinge because it just tilts up like that. And people play around with this stuff. You can buy it. Maybe your kids played around with this if you have them. Go to Joann Fabrics. Okay. Now, you can think about how much force could you generate, or how much torque can you generate about this, in this hinge. So let's say there's some amount of force that's going to be generated by a given length of this marker line. Okay, that's property of the polymer, of course. So do that. Heat shrink too big, same thing. Right? So there it is. So let's say we have 5 units worth of torque that can be generated if I just draw a single line. But if I go in and I create additional cuts and put additional lines in here, then what happens then for the same global angle that I twist, turn the hinge, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 units worth of torque that I could generate in here. So there's kind of a multiplication. Now, in principle, this could be shrunk to very, very small scales. So here are some micrographs from Nick Kotov's lab that Terry Hsu made years and years ago when we had this collaboration. And this is now using graphene sheets, graphene oxide in this case, sheets, and using focused ion beam milling that can get down to really, really tiny scales. You can take it down to 10 nanometer length scales with this machining technique, if you will. And with a combination of different materials, you can realize potentially the same kind of deformations. I wish Kamal was here because there's some interesting antenna concepts that you could realize using this approach. One of the folks in electrical engineering, Tony Gerbeck, and I talked about this actually at some point. Tony came up with this meta surface where the reflectivity is very angle dependent. And you could actually you could create like an optical diode where light goes in one direction, but not in the other with these things. And it turns out they're really, really difficult to make, especially if you want to go down to shorter length scales, because the size of these loops and rods that are intersecting has to be much, much smaller. It has to be in the order of the wavelength of light that you're, or smaller that you're using. So manufacturing this is very, very hard, but we can create effectively the same kinds of structures using this approach and cross-plane deformation that results simply by stretching this. So, okay, what else? And I think I'll finish here. You can see this is happening at a macroscopic scale, but what if we now start to miniaturize this and actually, make like a gym for human cells? Why would you want to do this? Well, it turns out, I'll give you one example why you might want to do this. People that develop cancer drugs have to make sure that those cancer drugs aren't disrupting, for example, heart function. So all cancer drugs that are being developed have to get tested for cardiotoxicity. And they do this typically in mice, But mouse heart is different enough from human heart that it doesn't actually predict necessarily what's going to happen in humans. And the idea that folks are working on now here at Michigan and other places is to actually take patient-derived stem cells, differentiate them into cardiac cells, grow them, multiply them, and create miniature cardiac heart tissues. Make arrays of these things and then put different drugs into different wells and see what happens to the natural contractile rhythm that these microtissues actually exhibit. Not only that, you can pace them electrically and see the response. So you can make tiny little gyms where the cardiac cells will span these little pillars, grab onto the holes that are made in them, contract. You can electropace them using electrodes that are defined in the making process, right? And then put it into little assay plates and test the performance of different drugs. I have a colleague just down the hall from me, Claudia Labelle, who works on lung organoids. So she works on cell assemblies that mimic the alveoli of lungs. And the same idea, you could test drugs and other things, how they impact that. But there, what's important is not the contractile forces so much as the shape and the curvature. Because if you think about the lung alveoli, right, in the human lung, is tiny little pockets, little cul-de-sacs. And it turns out that recapitulating that curvature and also the rhythmic expansion and contraction makes a big difference in terms of what you actually measure, what these cells then do. Okay, so it's kind of interesting. We have some other efforts in our lab to couple drug printing along with this to kind of accelerate these kinds of assays rather. But in the meantime, I think there's something interesting in this approach. It's I don't have a I don't have a monopoly on this approach, but it's a lot of fun, and you can start hopefully thinking using this approach to solve other problems. And I would love to talk to people about the problems in a different space and maybe start exploring even metamaterial effects where it's the geometry and the symmetry of the array and the collective effect of that structure in how it interacts with the fluid that begins to impact flow and so on.
Thanks, Mitch.
Yeah. Yeah, some questions. Let's start here and then go back there. Yeah.
Thank you. Sort of fascinating talk. I was just wondering, because a lot of applications are reaching, for example, the solar application. Sometimes there might be a lot of forest poles traveling big students for you or for animals, they have stuff needing stuff repaired.
Yeah.
Are you thinking about using these structures, maybe expanding in different directions with development stuff that you're carrying? Well, for the structures.
Yeah. So now we have so I have a colleague, Professor Tateja, who works on anti-fouling surfaces, and they go about it basically using some combination of chemical functionalization and patterning, for example. But also there's this effect of strain and differential strain that breaks up the interface between the foulant and the actual surface that you're on. Problem with a lot of this is that the surface could be quite large and quite rigid, and so there isn't really enough deformation to actually make it work over the scale that you want. And it's possible that putting in intentional defects like this will create local microscopic stresses and strains that will deform the interface in a way that will get rid of the foulant. The other possibility, of course, is that you can have piezoelectric and other kinds of, effects to get rid of the debris. I know something about devices and the materials and now making these structures. If you know something about the nature of the foulant and the problem that you're trying to solve, I would love to discuss further and see what we could put together for that. Yeah. Question back there first.
Thank you very much. Excellent presentation. I just had a question about question like But we can make these cuts. Does it lead to degrees of heating? Like this heating gas, filling gas, not carbon.
Oh, you're thinking in terms of the bottlenecks, sustaining heat, right? So if you think about the efficiency of a solar cell, right? The sunlight is incident on the cell. Power density, 30 milliwatts per square centimeter, kilowatt per square meter. And even if the cell is 40% efficient, you also where did the other 60% go? Right, 40% comes out as electricity. So a lot of it is heat. So these solar panels can get quite hot, and you're right, if I reduce the amount of material that's in contact with this ultimately heat, that could be a problem. And the problem gets even worse for concentrated cells. So when I'm showing results for concentrated UV cells, in fact, what's happening is that it's being limited by the performance, becoming limited by the temperature of the cell. We had factor of 8 pocket concentration, but the power concentration was down at 60 x. And part of it was that the full factor was coming down. And that was coming down because of the temperature went up and efficiency went down. So that's an issue. We have some other designs where now the element can be synced to a plate, like an aluminum or copper plate. And then the optic sits around that and you just move the optic. And so there's interesting ways around that. Like you're absolutely right. It's an issue that you need to start taking there. We have some ideas for actually managing heat in like battery-based systems, because charging and discharging is kind of a funny problem, right? Like on one hand, you want to keep things cool, except the batteries are moving ion. So actually having heat helps do that faster. So if you're doing fast charging, you need to heat things up. But too much heat during operation is not normal operation. So you need to be able to manage this band.
So you showed a slide and talked about your Kamal.
Kamal said right name.
So can you make these small buffers and be a project in the film around the area? Regular cross section or something like that, like the radio scanning.
Possibly.
So you can make how small can you make these little?
Well, I mean, like how much are you willing to pay for tiny clean room, for example, right? That will bring down the length scale quite a bit. Lasers can easily take it down to about 20 length scales. You can laser patterning, you can do lithography, conventional lithography, just regular optical, UV lithography can take it down to fractions of a micron. X-ray lithography and ion beam patterning can take it down to like a 10 nanometer length scale. And people are actually even playing around with using DNA to control where things bind and flop and save. So you can potentially take this all the way down to the length scales. But I would imagine if you're talking about antennas and radio frequency communication, or maybe like just optical, you don't have to go too much below a mic. Right.
Excellent. Really interesting. I had a few questions.
Yep.
First one was, hydroacoustics is about 15 years old. Origami, the kirigami services in the president behind. I was wondering if you change it, is there an internal reflection of, I was imagining an acoustic wave, and it was. Could you get it to reflect from one surface and in the global sense create local internal reflection by the controlling the acoustic impedance of the base surface and then manipulating the actual so very little goes back.
Yeah, I think that's quite possible. Yeah. And there's a couple of different ways, right? You can redirect and you can dissipate.
Yeah.
And so if you have, for example, under normal circumstances, let's say you don't have a lot of material, you're just looking at perpendicular, let's say, transport of energy, you don't necessarily have a lot of material within which you dissipate all of that energy. So if you redirect in plane, then you all of a sudden have a lot of info. So that's one interesting thing. The second thing is, about mechanical metamaterials, you can create structures with negative differential mass, for example. And so as you begin to redirect energy, you can engage some of those modes where you have local vibrations, but no propagating vibrations. So you can create trapped modes.
Something like that.
Yeah, absolutely. So I used to actually do quite a lot of, photonic design, right? And look at Maxwell's equations. You use Maxwell's equations to predict propagation of electromagnetic waves through media of different refractive indices, different absorption coefficients, and so on, right? So we generated omega K diagrams for electromagnetic wave propagation interaction with these materials, and in some cases active materials, whether it's solar cells or LEDs, like emitters. So you put in oscillators into these structures too, to then get nonlinear effects. And so, yes, absolutely, you can create. So we used to calculate this thing for optical structures that are now, a lot of that is actually part of the design in the OLED and trying to make it more efficient, is to take trapped modes and get them to come out. So there's absolutely analogs of that. Yeah.
The other thought was the ones on the electric field, but then the other was on the looked like a spiral, then you had strain gauges on it, and then you showed the example of the muscle tracking the real.
Yep.
So does this, so that if you have a compliant surface, like if a panel is something that's deforming,
Yeah.
does something like does something like this have advantages in measuring so the local strain rate, local deformation on surfaces that are compliant, like a compliant panel?
Yeah, and I think we maybe discussed this a little bit some months ago, is that you can create, there's different ways of doing this. You can put piezoelectric elements, resistive elements, capacitive elements, optical elements, and so on. What you get from this is that you allow the structure to show you what the localized stress and strain are, and then how it's distributed over the whole surface, right? So I could define lots and lots of these kinds of strain gauges. Here, we're just buying stuff off the shelf. We're not making this custom at all. But you could easily see how using photolithography, I can define these little gauges to be everywhere around the structure. And so then whatever the local deformation would be, then you read it out. Then you get into some of the nuances of actually cleaning the signal and extracting the signal, because sometimes you're going to get current, sometimes you're going to get voltage, and then you need to kind of play tricks with that. One of my colleagues, John Kamissis at Columbia, actually is really, really good at doing that. And I'm sure there's folks here that do that too, in terms of circuit design. Yeah.
One question was, why do you have any thoughts on why needles evolved to that current shape and not to something that looked like that folding ring?
Oh, well, so
I mean, I can see from a hydrodynamic perspective, but since it relies, is there an efficiency, some argument, some variation?
yeah, the yield, it seems, and again, I'm not a biologist, so I don't know too much about it, but I do have, I pretend like I, know something about it by giving one lecture in my intro to engineering class on biosensing. Right, so there's, biology has mechanisms for sensing electric fields, obviously light and sound and all that stuff for sensing magnetic fields and so on. And it turns out that there are some core structures that are conserved, if you will, across lots and lots of different kind of species and kind of niches in biology, because it works really, really well. So it turns out that, for example, electrosensing organs in fish and also pressure sensing organs in fish, like the lateral line in fish, so fish, they have this thing called the lateral line that senses kind of local pressure fluctuations, and that's kind of like how these schools of fish can react so quickly in unison. It turns out that there's like a little structure in there that resembles like a mini retina. And there's like a little follicle that sits in it, and pressure fluctuation locally gets translated into an electrical signal where it sits inside of that. And the eye actually has also kind of a structure that eventually evolved into something like that, and then light hits it, and then that gets converted into electrical signal that's transported down the nerve, right? So a lot of these structures are kind of repeated, reproduced, and so on. So polarization and depolarization of cells in response to some kind of stimulus is a ubiquitous thing that happens in animals. And similar mechanisms are used in like muscle contraction, right? You have like the junction and that gets polarized and you get a nerve impulse. So there's something that just, okay, you need an animal to have the shape that it has. But the underlying structure is kind of like there for the ride, I think, because it exists in a bunch of different animals, like muscle tissue. Like, for example, if you look at heart tissue, regular muscle tissue, it's actually a bunch of little cells, heart tissue, like a bunch of rod-like cells that are stuck together end on end into fibers. And these fibers come in bundles. And so then you're like, okay, well, now I have the same morphology, but now the cell is going to do this kind of polarization. But, I have to say, I'm talking out of my, because I'm not a biologist. You probably want to engage a biologist to truly understand that. But to me, I just see design, like the same design principle being used again and again.
Yeah, we should, thanks a lot, next meeting, probably stop. Each other.
Yeah, great.
Thank you very much.
Yeah. Okay.
Really cool. Really cool. So we recorded it. We'll plan to put these things on YouTube and all that. So
Oh.
folks that come on like this can see.
Cut the Q&A because I'm BSing a lot in the Q&A.
Yeah. Yeah. But yeah, if you have like 5-10 minutes, we get some food for you since you're.
Yep.
So
Oh, yeah,
come back.
yeah, appreciate it. Yeah, I should probably end the